So I'm going to describe what big O is. Oftentimes it's written with a big O like this, hence its name. It's an asymptotic upper bound, meaning that for large N, it will bound from above the function that you prescribe with this big O. More formally, it is a set of functions, in particular a set of complexity functions, as I'll mention in a moment. So anyways, here's the definition of big O. So I'm going to let there be, so let F and G be complexity functions. So I'm going to let F and G be complexity functions. And what am I going to do? What I want to do is I'm going to define what big O is. But I'm going to state it in terms of a biconditional statement. This is an if and only if statement. That means whatever I say on the left side of the if and only if this is true, then the other side must be, and these are naturally equivalent statements. So if one side is true, the other side is true, the other side false, then the other side is false. Gotcha? So the point here is that I'm going to say F is big O of G if and only if. So whatever, if this is true, then whatever I follow with this if and only if, so this is an abbreviation for if and only if. Logically, it's written as a bidirectional arrow like this. So this is to say that if I could go from this to this, these are logically equivalent steps. I can go from this to that. Because if this is true, that also is true. Okay? So, if and only if there exists... Now, I'm going to be very formal here because I like to make it so that you really can see some of this nice fancy notation. So, whenever I write there exists, this means, it doesn't mean that there for any instance it is the case. I'm just saying that there exists at least one of the following. And normally this is written with a backwards capital E. So this means there exists. There exists. C. So C is going to be a variable. It's going to represent a positive real number. So this blackboard R represents the set of all real numbers. When I indicate with a plus, it means positive. So it means we're not talking about -1, we're not talking about -2, we're not talking about 0, we're talking about things like 0.1, 0.2, 5, 10, but not things less than or equal to 0. So there exists C, and also another constant we're going to refer to as N0, which is going to be a positive integer. So similar rules. This is the set of all integers. So these are your counting numbers. So things like 1, 2, 3, but also negative numbers like -1, -2, -3. But this plus here indicates that it's only positive. So anything that is not 0 or negative. So it's only going to be strictly positive numbers. Things like 1, 2, 3, and so on. So there exists these. And I must stress that these are constants. So these are not, this is not meant to be, so these are constants. So these are not like things that vary. You fix these. Your job is going to be to find these. C and N0 such that, so this is what we call an existential statement. There's two variables. You can technically write two existential quantifiers here. But we're not going to worry too much about that. The big point here is that you're going to have a C and you're going to have an N0. Your job is going to be to find these such that, so you find C and N0 such that the following has to be true for all, such that for all N greater or equal to N0, it must be that F of N is less than or equal to C times G of N. So, what do I mean by this? I mean that if you give me the C and you give me an N0, it has to be that no matter what N I get that's bigger than or equal to N0, remember this is a positive integer, it must be that F of N is less than or equal to C times G of N, regardless of what N is, as long as it's bigger or equal to N0. The way you intuitively can look at this is like if I had my N and my N squared. So remember I had F and G before, where I imagine I have a line, and I had a quadratic. naturally, the way you can look at this is imagine I had some c, like just for simplicity, I'm just going to assume like c is 1. There's a point where these two functions intersect one another later on. Remember, n0 can't be here. It has to be a positive integer. So if I pick n0 to be right here, notice that everywhere after this point, this function here, this quadratic n squared, always will dominate. It dominates the linear function. Sometimes they say dominates. That's a technical phrase. So this is what the definition of big O is. So hopefully this helps. So I'm going to do an example. I have to do an example because I have to like bolt because I'm going to be attending an event. So we're going to use an example. You're going to find that this is rather simple. So it looks a little daunting, but really, remember, this is not too terribly complicated. All you have to do is think about the rules of the definition. So it's asking an existential question. So what does that naturally mean? You just have to demonstrate that they exist. You don't have to show that it's no matter what C and N0 are, it's that that there's a C and an N0. So I like to say that there's a game plan that you have to use. So when I talk about this, you'll find very often that I describe what I have to do, then I go logically step by step to derive what ultimately should follow logically as the definition of big O. So let's go back to that example that I was doing before. So here's an example. So imagine I have f of n is, say, n, and g of n is n squared. We're going to keep things very simple. So what do I have to do to prove that the following statement? I want to prove that n is big O of n squared. How am I going to prove this? Well, I use the definition. So I use the formal definition of big O. So how do I do this? I just use the definition. So remember, I said that f of n is big O of g of n if and only if there existed those c and the n0 such that for all n greater or equal to n0, f of n is less or equal to c times g of n. You'll find that very often this definition becomes very easy to remember once you do it many, many times. Usually by the time you're done with me, usually it's melted into your brain. And that could be both a good thing and a bad thing, especially if you want to do other things in your day. So how do we prove this? So here's a proof. So first I state what I'm going to do. So remember, before you sit down, you should maybe think about what you're going to do. So what's the game plan? So I like to call it the game plan. So I'll say, we need to find constants C, which is a positive real constant, and n0, which is a positive integer constant. Remember, these are real numbers. Sorry, this is a real number, and this is a positive integer. So you can't use 0 here. It must be something like 1, 2, 3, and so on. You're counting numbers. So, such that for all, make sure you put your commas in. Proofs also have to make some structural sense. Such that for all n greater or equal to n0, n has to be less than or equal to c times n squared. So, naturally, what you want to do is, this is usually the best strategy I find. You pick an appropriate c, then you find n0. Find an n0 that works. Now, naturally, we've seen that c is not very hard to find in this example here. So what I'm going to do is I'm going to just pick some c. You can try different ones and see if they work. I'm just going to pick something rather straightforward. I'll pick c is equal to 1. Then, remember, now I have to say what I'm going to do. Now we need to find n0 such that n is less than or equal to n squared, comma, for all n greater or equal to n0. Do you see any algebraic step I can do here to make this greatly simplified? Well, what I recommend is dividing both sides of this inequality by n. So I'm just going to say divide both sides of the inequality by n. Then what? Then I can say n is less than or equal to n squared is equivalent to me writing that I'm going to divide n on both sides. So what happens? If I have n here and n here, that becomes 1, and this should cancel at that squared there. So you end up with n is greater or equal to 1. So what does this mean? This means that that inequality is going to be true for all n greater or equal to 1. So what should n0 be? So I'm going to choose n0 to be equal to 1. So I have a c and I have an n0. Do you see where I'm done? I'm done now. So now I have to make a conclusion. Therefore, by selecting such a c and n0, by the definition of big O, n is big O of n squared. And I use this box to indicate that I'm done my proof. So by doing this, now I've proven to you that n is big O of n squared. So I want you to think about, because we're going to end up here, I want you to think, what values of c could I use for a corresponding n0? Are there any values for c for which I can't use what I just did here? So I want you to think about, are there different values of c that I can use such that there exists another n0? Likewise, do there exist certain n0s where c's can't be used? I want you to think about that with this example. So I think this is the perfect place for me to stop. So hopefully you enjoyed this. So I say thank you very much and have yourself a beautiful day.